In this video, we will see the definition of an invariant subspace being cyclic with respect to nilpotent transformation. Invariants of a nilpotent transformation are unique, and the two nilpotent transformations are similar if and only if they have the same invariants. First, we have the definition. If T is a member of A of V, which is a nilpotent transformation, then a subspace M invariant and a T of dimension M is said to be cyclic with respect to T if these two conditions are true. The first one, M T bar M is singleton 0 and M T bar M minus 1 is not equal to 0. This should not be 0. So we have the second condition. For Z and B, Z is a T and so on is a T bar M minus 1 form a basis of capital M. Now from the above definition and the theorem, it can be easily seen that if N1, N2 and so on are invariants of nilpotent transformation, then V in the theorem we have established this V1 direct sum, V2 and so on direct sum VR, where each Vi is cyclic with respect to T. These conditions were true there. So instead of elaborately telling that, it is enough we say that each Vi is cyclic with respect to T. So we have the next lemma, which states that if M is of dimension M and is cyclic with respect to T, then dimension of M T bar K is M minus K. M, capital M is of dimension M minus this one. So to prove this, we shall consider an arbitrary element x in M T bar K, so that x can be written as small m, the image of small m and T bar K. Where is the small m? It is there in capital M, being generated by, or rather this n has got z as a t and so on is a t power m minus 1 as basis elements. This m can be uniquely written as the linear combination of the basis elements like this. And when we apply t power k, because t is a linear transformation, this can be done. This is what we have. Now in this, up to this term only we have, the rest will be 0. The reason is m t power m is 0. So capital M t power m, whatever may be the element in capital M, when we consider this, they all become 0. So from the next term onwards, from this term onwards, we will have only 0. So this mt par k, okay, this is an arbitrary element in mt par k, and that is spanned by this, and this being a subset of z and so on is t power m minus 1, they are linearly independent. So linearly independent and they span, and therefore these vectors form a basis of mt par k. And so they are m minus k in number, so dimension of mt par k is m minus k. And why this step? They are linearly independent in M and hence in mt par k, because M is invariant under T. So next we have this proposition that invariants of nilpotent transformation T are unique. Now we'll consider T to be nilpotent transformation, and if possible, let us take N1 etc. Nr with this, and M1 etc. Ms with this condition be invariants of T. We would like to prove that how many such numbers, if there are R number, S in number here, R must be equal to S, and not only that, each one individually they must be equal for all I. Now from the remark what was made just now, V is the direct sum of VI's, where each VI is cyclic with respect to T. We have dimension of V to be N1 plus and so on NR, and V is also written as a direct sum of UI's, where each UI is cyclic with respect to T, and dimension of V is M1 plus M2 and so on MS. Now suppose I is the first integer for which Ni is not equal to Mi. So for convenience sake, we shall take, for definiteness we must have either Ni not equal means this is greater or this may be greater to this one. So Ni greater than Mi. We shall name this as statement P. Now we'll consider Vt par M, and that is we have our V to be direct sum of V1 and so on Vr. So Vt power mi rather, Vt power mi should be, we are applying t power mi on both sides. So this is what we get. V1 t power mi plus and so on Vr t power mi. So we know that dimension of a plus b is dimension of a plus dimension of b minus dimension of a intersection b. But dimension of a, this one. But when we have the direct sum, we know that this is singleton 0. So we'll have just here dimension of a plus b to be dimension of a plus dimension of b. So dim a plus b is dim a plus dim b minus dim a intersection b. But when we have direct sum, we'll have only dimension of a plus dimension of b. So we have dimension of Vt power mi to be dimension of V1 t power mi and so on dimension of Vr t power mi. And this is of dimension n1. So by the previous lemma, this is what we get. n1 minus mi and so on nr minus mi. Now, suppose I have a number, say 10. It can be 7 plus 3 or it can even be 10 plus 0. So whenever you have z which is like this, it can fall under this category or this category. So clubbing the two, we can have z to be greater than or equal to x. So based on that concept, we have dimension of Vt power mi to be greater than or equal to n1 minus mi plus and so on ni minus mi. The previous one had we written, it would have been ni minus 1 minus mi. This is the last term. This is named as 3. Now we will go to v being written as the direct sum of u1 etc. us. So when we consider same Vt power mi, this is I, we have I. This is what we get. And like the previous one, this is what we have. And in fact, just the lemma when it is applied, this is what we get. But actually speaking, these subspaces themselves will vanish because of the discussion here. We'll have the explanation of that. So here we are writing as such dimension of Vt power mi as m1 minus mi and so on. We have here mi minus 1 minus mi plus the rest of the terms themselves will be 0. Explanation is given here. Here we have the explanation. So dimension of Vt power mi up to only from ni is not equal to mi. So that means up to I minus 1, from 1 to I minus 1, n1 is same as m1 and so on. Ni minus 1 is same as mi minus 1. So because of that only we are getting this step. This is what we get. Right. Now, why these terms are themselves 0? They are not present, so actually dimension becomes 0. The subspace itself is singleton 0 and therefore dimension will be 0. The explanation is given here. Now we'll have the explanation. Before that, um, dimension, the ni minus 1 minus mi, up to that whatever I have, I am replacing that by dimension of Vt power mi. So this step becomes, up to this we have, the last term is only this. So the whole lot is replaced by dimension of Vt power mi. And the next one is ni minus mi we have. And these two will get cancelled, giving mi to be greater than or equal to ni. But that's a contradiction to statement P, because in statement P, this is what we have. So that means our assumption that ni greater than mi cannot be right, and the same way mi cannot be greater than ni. So there is no other way, ni should be equal to mi. So that is how the proof concludes. But now everything depends on saying that why this is 0. So for that we will consider this one. we have naturally 1 less than 2 less than 3 and so on. And MIs being invariants is what we have. Now suppose we have the values for them, say 7, 6, 5, something like this. Then U1 is cyclic with respect to T and is of dimension M1. So you have by the definition U1 being cyclic with respect to T, U1 T power M1 should be singleton 0. And my M1 here is 7. So U1 T power 7 is singleton 0. How about U2? U2 T power M2 is singleton 0. What is M2 here? 6. So U2 T power 6 is 0. When U2 T power 6 itself is 0, U2 T power 7 should be singleton 0. And in the same way, U3 T power M3 is singleton 0 because U3 is cyclic with respect to T and subdimension M3. So U3 T power 5, here M3 is 5. So U3 T power 5 is singleton 0. When U3 T power 5 itself is 0, U3 T power 7 should be singleton 0. So we have, when we consider this, U1, U2, U3, they all uh, when applied with T power M1, they become singleton 0. So because of this concept only, we have UI T power Mi 0 means you have UI plus 1 T power Mi to be 0 and so on. So because of that only, the term dimension becomes 0. Subspace itself becomes 0, so dimension becomes 0. So this is what we have. And when we substitute that in 3, we get this. We get a contradiction to statement P. So similarly, this is not possible. So we are left with only this Mi equal to Ni. So that shows that invariants are unique. Now, in the above proposition, it has been proved that if these are the invariants, then the matrices, they can be similar only if R equals S and each Ni equals Mi. Now, we have this theorem 6.5.2. Two nilpotent transmissions are similar if only if they have the same invariants. We'll name this as statement P and this as Q, so that we need to prove P implies and implied by Q. So first, to prove P implies Q, we use the concept contrapositive statement. So P implies Q is same as not Q implies not P. So not Q means suppose they have different invariants. Let S and T be any two nilpotent transmissions having different invariants. Then by the above remark, matrices of S and T cannot be similar. So conversely, we shall assume, so here now Q implies P, we have to establish. Q means they have the same invariants. So suppose they have the same invariants, namely N1 greater than or equal to and so on greater than or equal to NR. Then by the basic theorem in nilpotent, we have bases, say V1 etc. Vn and W1 etc. Wn of V, such that the matrices of S and T in them are each equal to Mn1, Mn2, Mnr. So we have S basis matrix, T basis matrix. Suppose for convenience sake we write the entire matrix as simply the matrix with entries alpha ij, say. Now let these bases basis elements be taken to these basis elements by a transformation, say A. So VIA equals WI. Then we are going to show that S and T are similar. So for which now we have the matrix of S. We have the matrix of S in the basis. So matrix of S in the basis is alpha ij. In which basis? This one. So how it could be written? VIS is equal to summation alpha ij Vj. And similarly, matrix of T in this basis is again alpha ij. So how it can be written? WIT is equal to summation alpha ij Wj. So now you consider this WIT equal to summation alpha ij Vj. So here the Wi is replaced by this one. wi is replaced by this. So suppose I put it as say star. So using star and this one, we have VIA T equal to the summation alpha ij. Wj we have that is replaced by the star VJA. A being linear transformation comes out. So we have this, and we know already that whenever a linear transformation takes a basis to a basis, then that must be 1 to 1 as well as on to. So its inverse exists. So we apply A inverse on both sides. So we get EI ATA inverse to be this. But summation alpha ij Vj is VIS. So what we have is VI ATA inverse to be equal to VIS. As the transformation agree on basis elements, we should have the transformations to be the same. ATA inverse should be equal to S, which means S and T are similar. We have S and T to be similar. And this question can be asked in section B for 5 marks. Thank you.